some of you are gonna probably figure it out, and some of you might not. What I hope is that the process of discovery is still fun. And I'll be really clear that my expectation is that you're gonna just play around with stuff, and you're gonna try some stuff, and you're gonna make some measurements, and then if you get it, great, and if you don't, no worries, because I'll talk you through it next week, so I'm not gonna abandon you. I might even, depending on how quickly things go, I might even talk you through it today, so I'm not expecting that you're gonna figure it out. You won't be out of luck if you don't, so hopefully you can find it to just be, I don't know, if you've ever done like one of those brain teasers where you're trying to figure it out, and you're trying to figure it out, and you just can't do it, and but it's still fun just to try. That's kind of how I hope this feels to me. Two quick announcements. One, if you've got your Chromebook open, will you close it? And two, progress grades. I went ahead and posted those this morning. If there's one or two things that came in, at some point yesterday and I missed it, these aren't a big deal. So you should still check your grades. If something doesn't look right, let me know. But at this point, progress grades are going out with whatever is in Canvas right now. And if you aren't happy with your grade, please come and talk to me, because it would be sort of an individual thing, but I would love to help you. If there's anything that I can do to help you learn what you need to learn in order to get your grade where you want it to be, I'm in. But I need your help with that. So come find me, talk to me, and we'll get that figured out. And let's see. So what I'm going to do today is start with the where we left off the other day. We were talking about these free body diagrams. And I'll just put this up here for a sec so you can refresh your memory. But basically what we were doing is looking at these free body diagrams and thinking about how we could draw just a symbolic representation of an object and then draw arrows showing all the forces that act on the object. And forces are vector quantities, which means they have a direction. We live in a three-dimensional universe, three spatial dimensions, which means every single force can be thought of as having a three-dimensional component, right? Like there's part of it that's this way, part of it that's this way, part of it that's this way. We're mostly going to deal with forces in two dimensions just because it's so much easier to draw. Every once in a while, we're going to have to think about three-dimensional forces on objects. If objects are moving in three-dimensional space, we might have to consider those. Usually, our free body diagrams are going to look like this, where we think about our forces as having one or two parts. Either they're completely in one dimension, or they're completely in another dimension, or they're at an angle to those two dimensions, in which case we can think about them as having part of the force in one dimension and part of the force in another dimension. In other words, we're going to use the vector solver and vector math to combine forces and to split forces into pieces so that we can more easily analyze their effect on objects. So we're going to start simple today, and then things will become more complex because not all forces neatly align themselves into 90-degree angled components. So we're going to have to do a little bit of math to work with these. But to start with today, we're going to keep it simple. So let's look at a chair at rest on the ground. So this is not a free body diagram. You can draw this along with me, but just know this is not a free body diagram. This is an exceptionally realistic picture of a chair on the ground. Okay? And it's not a free body diagram because free body diagrams show one object at a time. This is already showing two, and doesn't depict the objects like this, but this is what we want to draw. Okay? The chair is at rest. So if we were going to draw a free body diagram of the chair, here's how we would do it. We would start by drawing a box representing the chair. I'm going to draw this box so that it's oriented horizontally because my chair is kind of oriented horizontally. forces that are acting on this chair, well, think about all the forces that we talked about the other day. We talked about weight, which is the force from gravity. We talked about tension. We talked about spring forces. We talked about friction. We talked about normal forces. So what would be the forces acting on this chair? Well, it's on Earth. Everything on this planet is being pulled down by gravity. So there is a force downward on our chair. We could label this if we want, chair. That force, we're going to label this arrow. This arrow represents the force of gravity. I'm going to represent that as a capital F with a little g. This is usually what I'll do. Because we're on the surface of the Earth, that will be equal to the chair's mass times g, the acceleration of an object in the Earth's gravitational field close to the surface, which is 10-ish meters per second squared. What are the other forces? Let's kind of go through the list. Are there any strings or like springs? I don't see, like, we're not told, so let's not put any strings or anything like that. What else?
The ground pushing back. I don't know if that would be the normal force.
So the normal force, and yes, that is what's going on. Let's come back to that in just a second, though. Let's think about the other ones. What about friction? How do we know if friction is acting on the chair? Here's how I think about it. I imagine if the chair were on wheels that were virtually frictionless, would it start moving? And I mean, in real life, is the ground perfectly horizontal? No. In real life, if we take things that are completely frictionless and put them on the ground, there's a chance that they will start rolling because the ground probably isn't perfectly level. But in this theoretical problem, let's just say the ground is level. So no, it wouldn't. Like, you could put things on wheels on the ground and they won't roll unless the ground is tilted. So let's say the ground isn't tilted, so there's no friction. We're not told that there's a person pushing or pulling or an antelope pushing or pulling or anything, so we don't have any other forces acting on this chair that we can readily identify besides this one. And then Lillian brought up, well, what about a normal force? What about the ground? How do we know that the ground is exerting a force on the chair? How do we know the direction? What can we use to deduce that? Yeah.
Because if there wasn't, then the chair would be blown down.
Right. Newton's first law says overall forces cause objects to accelerate. The motion of this chair should change if this is the only force acting on it. If this is the only force, it should be accelerating downward. It's not. The only way we can have an object that stays at rest is if all the forces acting on it are balanced. So there must be an upward force on the chair. It's got to be in the opposite direction of the gravitational force, and it has to be the same size. Otherwise, the chair would be accelerating. What's that force coming from? The ground, the surface, the floor. That force is at a 90-degree angle to the surface. The surface looks like this, the force looks like this. That makes it a normal force, normal meaning perpendicular. So there's our two forces. This is what your free body diagram should look like. Much of the time, when you have like you're working in real life, you're going to kind of have a reference frame implicit in your head where your one axis is vertical, one axis is horizontal. Sometimes we won't though. So it's always helpful to include a little coordinate reference frame. This is how I'm thinking about this. I'm thinking about this problem where one reference axis is perfectly horizontal, one is perfectly vertical, and those are the axes of motion and force and everything else that I'm going to be evaluating. Okay, so this is pretty easy. Let's look at another one. What about if we have an object suspended from a string, like this? And we're moving across the room at a constant velocity, like this.
That makes it spin.
It doesn't make it spin. It's spinning because the string is slowly unwinding. So you can ignore the spinning motion for now. It's not that that doesn't matter. It's just that that's not related to what we're talking about. What's going on here? Well, here's our object. This is, does anybody know what this is?
Electrical.
No, it's not, no, it's metal. This is called a Ranklin. A Ranklin.
Oh, okay.
Yeah, you didn't know that?
Well, I thought it was tape.
Huh? You use them to rankle things. So if you have something that you need rankled, you would just use the Ranklin for it. Any questions? Ranklins generally come in two sizes. So I have both. I have a small Ranklin S, and I have a large Ranklin. So we can use this, obviously, all know what we use the large Ranklin for, right?
Yeah.
If there's something large that you need to rankle. Okay? Duh. I mean, this is obvious stuff, people. Okay, I wonder what I'm gonna call it tomorrow in the second period. All right, so we've got the Ranklin, and we can look at this Ranklin and we can evaluate some stuff. This is my legacy. There is only one thing that you people are gonna remember from this class, and that is the Ranklin. Okay, so let's go through the same set of questions. First, we're on Earth, we're close to the surface. That means there has to be a downward force from gravity. Because of where we are, that's going to be equal to the Ranklin's mass times g, which is 10 meters per second squared. Think about all the other forces acting on it. Is there a spring? No. Is there a surface underneath it that's pushing up? No. Am I touching it? No. I am definitely exerting a force, but I'm not exerting a force on the Ranklin. So yeah, Trey, you got it. There is an upward force. It's from the string. And when we have forces from strings, or cables, or cords, we generally refer to that as tension. It's a pulling force. And I just use a capital T for that usually. You could do F with a little t, it doesn't really matter, but I just use a capital T. Now, this object is moving at a constant velocity, right? That means it's not accelerating. That means that the sum of the forces, the overall force, has to be zero. The acceleration is zero. The overall force has to be zero, which means these two forces, which are the only forces acting on Ranklin, have to be equal and opposite. There is no difference in the overall pattern of forces on this Ranklin as there were in a chair resting on the ground. If I hold it still, it stays at rest. If we move at a constant velocity, it's not accelerating. Now, if I do want to accelerate it, if I wanted to accelerate it in this direction, I have to somehow exert a force in this direction. How do I do that? By moving my hand? But doesn't the string move with my hand? I mean, if I move it in that direction, doesn't it just, like, how can I push this with a string? Can I push things with a string? It doesn't really make sense, does it? Here's what happens if you actually watch what's going on as I accelerate this. So you're gonna have to watch quickly, because in order to accelerate, I have to go faster and faster and faster. Watch what happens to the angle of the string and the Ranklin. You see that? Right as I accelerate it, watch what happens to the string. Did you see it? Tilted. In order for me to accelerate the Ranklin this way, I have to pull it, because strings can't push, which means it had to look like this. So that my string wasn't just holding it up, but was also pulling it to your left. And that's a little bit easier to see with a balloon. So if I accelerate this balloon, you'll see really easily that the string has to tilt. But here's what's really interesting is, what if I move with my balloon at a constant velocity? Let's see what happens. Uh-oh. What's going on there? Yeah, there's a third force. We didn't really have to account for it with the Ranklin, because the Ranklin is so heavy. But with a balloon, we do have to think about this third force. So with a balloon, here's the picture of what the balloon looks like, okay? Balloon is here, and there's a string here, and there's my hand here. This is what it looks like. What are the forces? Well, there's still the force of gravity, which is equal to the mass of the balloon times g. That's still straight down. The fact that it's a balloon doesn't change the fact that there's still a force pulling this balloon straight down toward the ground. If we just let go of it, it'll fall, just like anything else would in its gravitational field. Yeah.
But for the Franklin, would you not have to like add anything on either side for the free body diagram?
So there technically there is a little bit of air resistance here, but we can ignore it because it's so small.
I mean for the moving back and
You don't have to. No, not while I'm moving at a constant velocity. To get it to accelerate, I did have to pull it, and so what happened was my string tilted, and then I had an overall force in the direction of the acceleration. But that didn't last long because in order to continue that, I would have had to just move faster and faster and faster, and I'm too old. So I couldn't do it. With a balloon, it's a lot easier to demonstrate. So with the balloon, the string is in this direction, which means the tension has to be in this direction too. As I'm moving with a constant velocity this way, and not speeding up, there's no acceleration here, you can see the balloon is tilted with respect, the string is tilted with respect to the vertical. So this, on its own, can't be balanced. Because, like, we can imagine the upward part of the tension is going to be matched with the downward part of gravity. But what about this part of tension? There's some of this tension that's pulling it this way to the right in this picture. This should cause the balloon to accelerate. So there's got to be something else going on. Yeah.
Yeah, I was wondering for like when the string is not straight, would you draw it as like a diagonal line, or would you split it up into like two?
Either way is fine. Yeah, we're ultimately going to need to split it up into two pieces, but for now we don't have to. Yeah.
And then if you do split it up, would the tension going upwards still match the gravity down?
Wouldn't it have to?
Oh, okay.
Yeah.
What would you be doing?
Yeah. If we think about the upward part of this tension, it has to be equal and opposite to the downward part of the gravitational force. Otherwise, the balloon would be accelerating one way or the other. And it's not. So as long as it's not moving at all vertically, it can't be accelerating vertically, which means all of these up and down forces have to match.
Does that mean that you're putting in like more energy dragging it, like relative to its mass for the balloon than the Franklin, because it's like an extra tension thing?
Yes, if I were to hold the balloon straight up and down like this, there is less overall tension in the string than if I move it at a constant velocity. There has to be more force. There has to be a greater tension force in the string because this part of it has to stay the same. So we're adding a rightward part to our tension. What's balancing it out, as you already figured out, is air resistance. We don't really have a great term for air resistance, but we can just call it the force of the air. The air's pushing the balloon this way. The string is pulling the balloon this way. Those two pieces match. If we were to think about this tension force as having two parts, one of those parts would look like this, would be the same length as this. One of those parts would look like this, and it would be the same length as the air resistance. Okay, let's see. This is something we've already talked about, but just as a reminder, this is where it gets, we are going to run into this over and over and over again. We're going to see the forces and think about the forces that we're applying to something, but we don't necessarily see all the other forces. Friction, normal force, air resistance, those kinds of forces that there's no obvious like, oh, there's friction, I can see it, I can see something producing friction. So just recognize that what you do to determine whether forces are overall balanced or not is look at the motion. of an object. If it is accelerating, there has to be an overall force. If it's not accelerating, there can't be an overall force. So we can deduce from an object's motion something about how the forces must look. And then the last thing that I want to do is just give you some names, and this is stuff that you mostly are, like some of this we already know. We already know that when there's no acceleration, the overall force on an object has to be zero, because the overall force is equal to mass times acceleration, which would be mass times zero, so mathematically there can't be an overall force. The object's motion will remain the same, so it'll either stay at rest if it's at rest, or it will stay moving in the same direction if it's moving. Those things have names. Static equilibrium has to do with objects that are motionless. Dynamic equilibrium has to do with objects that are moving at a constant velocity. And unfortunately, when we start accelerating things, that is referred to as dynamics. So we've got this combination here. Dynamic equilibrium is a constant velocity. Dynamics refers to accelerated motion, and that's unfortunate. I'm not going to use this term, dynamic equilibrium, because it's confusing, but you may, I think it's in the book, which is why I just wanted to point this out. I'm just going to refer to things as being in equilibrium. Equilibrium means there's no overall force on an object, its motion will remain the same, okay? And equilibrium isn't like, there's a lot of things in equilibrium around us right now. You look around, anything that's not moving is in equilibrium. There's not much that's moving at a constant velocity, but maybe like an air particle is drifting at a constant velocity, or a little piece of dust is moving at a constant velocity, and those things are in equilibrium. And so equilibrium is a pretty common condition on the surface of the Earth, which means that we can establish equilibrium pretty easily. Setting things up in equilibrium is mathematically helpful because it can allow us to determine unknown forces. We'll come back to this in just a second. I just want to show you this example because in this example, let's suppose we had an object that was attached to three ropes. One that pulled up and to the right, one that pulled up and to the left, and one that pulled down and to the right. If we had measurement devices in two of those ropes, and the object were in equilibrium, it's not moving, or it's moving at a constant velocity, we could mathematically determine what this other force would have to be. And in fact, that's exactly what people do when they're, for example, designing a building. They figure out all the forces acting on the building, and then if they don't match up, they attach things to the building to make sure that they do. So there are usually our buildings nowadays are built with internal structures to balance forces. But in the old days, how many of you have seen old Gothic churches, like pictures, or they have those things that come out of the side that look like kind of half arches? Those are called flying buttresses, and those are supports for the walls. They're built to keep the walls from collapsing outward, because the forces wouldn't be balanced without those flying buttresses. The weight of the roof is pushing outward on the walls. You gotta have something else that's pushing in on the walls. So people use this idea of finding an unknown force to design buildings that won't collapse. We also use the idea of equilibrium when we need to find measurements of friction. And in this classroom, we're never going to find the friction of anything of importance. We're just not. Nobody cares about the work that we do in this classroom. Hopefully it's fun, and hopefully it's interesting, but it's not at all something that anybody needs to know. I promise you, nobody's ever going to ask us what the friction of our little wooden things with the weights on them. But what we're doing in this classroom is a multi-million or billion-dollar business outside of the classroom, largely for transportation, but we determine friction for all sorts of things. The biggest the application of the technique that we're using is with tires. We need to know the friction in tires that we are manufacturing. We need to know how they're going to behave on asphalt, how they're going to behave on concrete, even metal and wood, because vehicles drive on like metal bridge decks, and you know, people like, there's somebody in my neighborhood has that like a wooden driveway, like the driveway is like platform wood. We need to know what the friction looks like. We need to know how friction changes when surfaces are wet versus when they're frozen versus when they're dry. And so the way that they determine friction is very similar to what we're doing in class. They have much better equipment. They do hundreds and hundreds and hundreds of trials. They try all sorts of different vehicles, but essentially it's the same basic thing. You can't directly measure friction. You have to figure it out indirectly, and the easiest way to do that is to establish equilibrium. So that's what we did when we found friction with our carts the other day. Yeah.
So is there any way to know like how much of friction is like attributed to like its physical interlocking? I don't know if that makes sense. Versus like chemical.
Not really, no. And yeah, it does make sense, because if you were to zoom in on something, what you would see is that some parts of the surface are perfectly smooth, and what you're doing is kind of sliding them along each other. But there's also like little bumps and ridges, so you can kind of imagine like on a micro scale, friction involves this kind of stuff, right? Like there's an actual like bonking into something, and we can't figure out exactly what part is what. Some of it is like electrostatic, and some of it is purely mechanical. We don't know how much of each it is, but our models work really well for both combined. So luckily, we don't actually have to. So what I suggested is that you set up your carts like this, where you have the cart towing your little friction device, and there's some sort of a mass hanging over the other end. I suggested that the only forces that really mattered on this whole thing was our object, the cart, and the thing that it was towing. We're considering this to be our object. The only forces that really mattered were the tension and the strain and the friction acting on the object. I suggested that since the sum of the forces is mass times acceleration, if we can set up a system in which our object is moving at a constant velocity, the acceleration should be zero. The only way we can have no overall force is if these two forces are equal and opposite, in which case all you have to do is correctly measure the tension, which you can do with the built-in force sensor of the carts, and that will tell you the force of friction. When I did it the other day, you all saw me. I don't remember exactly what I got. I wrote it down somewhere, but now it's gone. I think I got like did I get like 3.5? Does anybody remember what I got? I think I got about 3.5. And what did some other people get? Somebody got 2.5, right? Roughly? Did somebody get 2.5-ish? Did anybody get anything that was like dramatically different? Like you guys did, but we figured out what went wrong with you, right? You forgot to calibrate your force sensor, so that's fine. Did anybody get a value that they felt was accurate, that was dramatically different from these? Right, so based on this, I'm going to say that the force of friction acting on our little thing here was about 3 newtons. Somewhere between 2.5 and 3.5, right? Probably not exactly. And different setups are going to have different amounts of friction. Different track, like the surfaces of the track aren't all the same, the surfaces of the wood block aren't all the same. Like, there are probably actual differences in the friction. But for the most part, this would be a pretty reasonable number. And this, it turns out, is going to be a really important first step in much of the stuff that we're doing. Because in much of the stuff that we're doing, what we want to do, what we're going to end up wanting to do, is make predictions that we can't make if we don't know how much friction is acting on an object. So often, the first step of the activities that we do in this class is going to be, first we have to find out how much friction is acting on the object. Once we know that, then we can make predictions about other stuff. And if you think about it, again, that's something that within the context of this classroom, nobody cares about it. Nobody cares about our little systems. But if, for example, you're developing in a printer, like if you end up working for an electronics company like HP and you design a printer, you better know how much friction is in those mechanisms, because the way those things work is those little print heads move back and forth spraying ink, and they're moving incredibly quickly. And if they're not where they're supposed to be, when they're supposed to be there, what comes out on the page is going to be garbage. What determines where they are and when they get there are the forces acting on it. There's gears and motors that are providing forces, but there's also friction. You can't get rid of it. So we have to know. We have to know what friction is acting on things before we can design and build and make accurate predictions. So what I'm going to have you all work on today, so there's two things you can think about. The first is, if you were not able to get a decent measurement of horizontal friction with our little setup, that's worth doing. And here's the thing, we now know roughly what it should be. So if you're not getting somewhere around 3 newtons, then something's probably wrong. So that's your first step. If you feel confident that you can pull this off, then you can try the next task. And the next task, like I said, this is a stinker of a problem. You actually, believe it or not, have all the information now that you need to solve it, but I haven't showed you how to put it together. Some of you will be able to figure it out. Some of you will figure it out more quickly than others. And some of you are going to do some stuff and you're going to come up with a number, and then I'm going to tell you that's not quite right. And what I want is for you to just play around with it. I'll help you when and if it becomes necessary, no later than next week for sure. But I also want you to have that experience of trying to figure it out. So here's your next problem. You're going to take a track. You're going to stack it up on a couple of those pieces of wood. Don't use the books, because they just end up on the counters and stuff and they're a pain. But there's a box over there, a cardboard box with a bunch of pieces of wood. You can put 1 or 2 or 3 of them to tilt your ramps. It's just these ones, these little pieces of cut up plywood. So you can tilt your ramps like that. And then we're going to set up the same system that we had before. You're going to have the cart. Your cart's going to be towing the same exact system. Our block of wood with 2 of those metal masses on it. There'll be a pulley and some sort of a hanging mass. And your goal is to find the force of friction acting on this object. And you might think, well, isn't it going to be the same? And it turns out it's not. It's going to be different. But what it's going to be is tricky to find, okay? So this is your goal today, to find the force of friction acting on, what we're really finding is the force of friction acting on this whole thing. This, just like before, this is our object, but because the wheels on the cart are so frictionless, the only friction is here. So we're finding the friction on this whole object, which turns out to just be the friction acting on this part of it, okay? It's a challenge. Do what you can. Come to me with questions. Play around with it. Hopefully you'll have some fun. And take a break before you get to work if you need one. So it's about 10:25 now. Come on back at 10:30 or 10:31, and let's see what you can do.